so it might be hard for him to come by, but he could like zoom to like tell you guys about some of the stuff he does. It's pretty cool. There. All right, so the idea of modeling is also called regression. And it's a major component of AP Calculus curriculum that we'll revisit throughout the course. So today we're going to be looking at polynomial models. We will definitely use this on trig models as well. So I know for sure we do those too. I can't remember if there's another one that's in there. So we're going to start with this first example here. They have given us age in weeks and weight in kilograms, and it tells us that the age in weeks and the weight in kilograms of 5 randomly selected babies from a particular pediatrician's office are listed in the table above. It tells us a linear regression can be used to model these data, where Y is the predicted weight of a baby that is X weeks old. And so it asks us to write the equation of the linear model here. So this is something you do as early as Math 1. We just need a refresher on how to type this into Desmos. So you can follow along if you would like on Desmos and put it in, or you can watch what I'm doing here for that. So let's shrink this back down. All right, so it is so much easier on the on Desmos than it is the calculator. The calculator takes forever. So if you want to do a regression of any sort, first thing you got to do is you got to put your data in a table. So you're going to hit the plus sign up here. You're going to click table. And you're going to enter that data into the table. So and it will show you a graph as soon as you start typing things in. Anybody remember what I do if I want to see that graph like better here? What do I have to click? I'm missing, because like there's 5 points. I'm missing one of them. I could zoom. That would work here, but there's a quicker way. This little magnifying glass over here in the corner, if you click it, it'll go straight, it'll like zoom into just the data points that you have. Sometimes it can be very helpful. Sometimes, like on that one, I did lose the x-axis whenever I clicked it. But especially if you can't see your data points, it's helpful to do that right there. And then you can zoom in and out as you need from that. Also, let me just flip over here and see if it's available. Let me put the data in this one. This is the North Carolina testing version.
What's the difference?
There are a few things that are restricted on this one. So, like, for example, if I want to solve an equation on this one, like if I've got 2x plus 3 equals 5, or let me do 15 so it's bigger, it will put a vertical line here, and wherever it crosses is your answer. But if I try over here, 2x plus 3 equals 15, it won't do it. It'll give you an error. So they have restricted that capability on the tested one, mostly because they don't want to be able to just for you to just type it in. Now there's still f of x, g of x, see where they cross that. It'll still do that. But it won't do this. So I wanted to show you here, I don't know exactly what the AP Precal one is going to look like yet, because I think I did get an email about that. I need to look into it more. I haven't had a chance to look into it. But they, on regular Desmos, they have added this button right here. And this button, if you click on it, you just have to click on it and it'll do the regressions for you. And then you have all these regressions that you can choose from. And you don't have to remember how to type anything else in. I hope that they are going to incorporate that eventually. I know for North Carolina, we got an email on that saying it will not be included this year. They will consider it for like they might include it next year. I do not know if that will be available to you on the AP exam. I'm leaning towards no, just because I haven't looked at it and it'd be safer to say no. So I'd like for us to not use that button right now until I find out for sure if we are going to be able to, if it will be there. Because if you look at the North Carolina one, it's not there. There's no button there. It's not an option for that. You can still do it. You can do the table. You click the table, you get this. Oops, let's undo that. So I guess I should probably use this version instead of the other, since I'm not going to let you do that. So, since if we do not have that regression part there, then we have to know the form of linear, quadratic, cubic, quartic. And for linear, which is what they've asked us for here, it's just y1 squiggle ax1 plus b. You're just going to type a y and a 1 right after it, and it'll automatically go to the subscript there. So you're going to type y and 1. It'll make it a subscript. The squiggle is going to be shift and that key up there next to the 1. And then ax1 plus b. If it gives you an error, most of the time you have either forgotten to do a squiggle instead of equals, or you forgot to put a 1 behind either your x1 or your y1 for that. And it automatically pulls up your results. It will give you down here your A. Look at that. I did this. I guess because I didn't do it in the North Carolina testing, I just did this Friday. And the format's different. This one's got A and B down here at the bottom, and the residuals up here, and this one does not, which is weird. I don't think I was using the testing one. I was probably using the other, so that's probably the difference there. Yeah, because it, in fact, if you got that regression button, it automatically plugs the numbers in for you there, which is nice. But that's not an option here. So we're going to go with this one. I feel like it's going to be closer. But our A is 0.185. Our B is 3.545. Here, these R and R squared values, R is known as your correlation coefficient, and it's telling you how close your graph is. Does anybody remember what number that's going to be if it's perfect? If it fits every point, it's going to be 1. Or -1 if it has a negative correlation, like if it's decreasing line. So if it fits perfectly, you'll get a 1 or a -1 here. This R squared is what you have to use to compare sometimes, because R can be positive or negative. R squared is always going to be positive. So a lot of times we look at R squared to compare results here. So for this one, our answer would be y equals 0.185x plus 3.545.
So you don't follow A plus BX, or is that what you do for the linear regression?
For linear regression, you're doing A plus A. We're doing A x plus b. Let's see. Over here, yeah. So A is like your M. It's your slope for that. All right, so what I also suggest that you do here is write down, remind yourself, x equals and y equals, and put what they stand for. When it gives you a table, it's pretty easy. X is your age in weeks, or you at least need to make a mental note of this, and y is your weight in kilograms. That helps me keep it straight when I've got to answer these next questions. All right, so part B asks you to use what you have found to answer questions about the situation. It says, using the linear model from part A, what is the predicted weight in kilograms of a baby that is 10 weeks old? Okay, so it is not asking you to use the table and guess on this. It wants the linear model, which means the line. There's several things they might call it. They might call it line of best fit. They might say linear model. They might say linear regression. Those all mean the same thing. So if we look back up here, X is my age. So it is asking us what happens whenever X equals 10. Right? The quickest way to do this over here is to type in X equals 10. It's going to put a vertical line right here. Look for where it crosses your regression line for that. And so it is 5.395. And that is the weight, and it is in kilograms. That is the quickest way. Other options, if X is 10, you could just plug it into the equation. So you could do, what was the equation here? You could do 0.185 times 10 plus 3.545 gives you the same number there. Okay. C asks you a different type of question. It says the weight of a sixth baby is 5.3 kilograms. Using the model from part A, what is the age in weeks of this baby? So this time it gives us a weight. Is weight X or Y? It is Y. So Y is 5.3. We want to know what the age would be. So I would clear out this stuff because it was for the last part of the question. And I would type in Y equals 5.3. It's going to put you in a horizontal line. You're going to see where it crosses the regression. And you get 9.486. So 9.486 weeks. It is possible to do this without graphing it. It just takes longer. What you would need to do is you'd have to do 5.3 equals 0.185 x plus, what was it, 3.545. And you would have to solve that equation for x. So, however, if they've asked you to do the regression, it's a calculator active problem. So, you're going to be able to just graph it and it'll be faster.
Is that on the top of this, like, why does it say a linear regression y equals a plus bx, but then we use, like, bx plus a for the,
Where at?
like, a, part A.
Uh-huh.
So, like, it says, like, a linear regression.
Oh, I need to address, yes, I didn't even pay enough attention to that. I don't know why there's a difference here. I don't know why they even sometimes have a plus bx and then sometimes ax plus b. I always do ax plus b, or you can even, like, a line is, to me, is y equals mx plus b. I've heard it. I could change this to an m, and now it's going to tell me m is that number instead. I guess I probably should have written this as 3.545 plus 0.185x because of that format. But all I would need to do here is switch those. If I type it in like they showed me here, then I would have a plus b times x1, and you'll notice it just switches the values you have for your a and b. Yeah, so it's the same line either way. I am pretty sure that even if you did write it this way, they would still accept it because it's mathematically equivalent for that. So the calculator also has that as an option. Like when you do linear regression, one of them is ax plus b and the other one is a plus bx. And I need to look into that more, why there's even two different options there, because they're the same. So it might have something to do with statistics where this is like a more standard way of putting it in
But
statistics, but
thing.
it's not going to matter for us. I just go with AX1 plus B because that is more like Y equals MX plus B, which I would think about. As long as you're putting your A's and B's with the right places, it doesn't matter. Okay, now this technically is a 2.6 topic. Residuals don't come in till 2.6, but since we're doing regression here, I feel like we might as well go ahead and do them. And so does Mr. Passwater because he put them here. So a residual is going to be a measure for a single data point that will tell us some information about that point. So when we use a model to predict values, we expect our model to produce values reasonably close to the actual values here. But our models are not expected to result in exact values generally. The difference between an actual value and the value predicted is called the residual. So when you do this, unless you have perfectly linear data, which you normally do not if you're just taking data points, then your points are going to have residuals. So if you look here, you can see like my green dots are not perfectly on that line. So they're off from the predictions just a little bit. A residual is going to be the actual value minus the predicted value. Okay, so that is something key for you to have memorized. Residual is actual minus predicted, and you need to know that order because this can be positive or negative. So actual minus predicted. Actual is the value that's in your table. Predicted is what the line gives you. So, for example 1, what is the residual of the baby that is 5 weeks old? Interpret the meaning of this value in context of the problem. So if I go to my table, there was a baby that was 5 weeks old. It was 4.4 kilograms. Okay? So my actual value comes from the table. I'll write table here. And it is 4.4 kilograms. However, the predicted value is what I get if I plug 5 into this line. Again, the quickest way to do that is just to say x equals 5 and see where they cross, which is 4.47 kilograms. Everybody okay there? So residual is going to be actual minus predicted. So 4.4 minus 4.47, which is going to give us negative 0.07. If you get a negative value, your data point is lower than the predicted, right? It's below the line right here. So in this case, we're talking about the baby that is 5 weeks old. So the baby that is 5 weeks old weighs 0.07 kilograms less than predicted. And you can start to see where this would start to become important. I would imagine, I'm no pediatrician, but I would imagine that 0.07 kilograms you're not too concerned about, right? Like if the baby is 0.07 kilograms smaller than what would be predicted by its age, that's not a big deal. Babies are going to be bigger and smaller based on a lot of different things. However, if I saw a baby that had a negative 1.9, that it's almost 2 full kilograms smaller than you would expect for a baby of its age, then you would maybe be more concerned for that. Probably on the other end, I mean, if you got a giant baby, maybe you're worried there's something wrong with it that's making it so big. You're probably not too worried about just a really fat baby at this point. When you get older, if you have a child who's in kindergarten and their residual is way positive, they're way high, then, that might be a concern moving forward for that child because it is probably already, overweight and will cause problems down the road. So that is, something you would look at. This is a very small data set. Whenever doctors, of course, would be looking at much bigger data set there and wouldn't be doing the data on their own. I'm sure it's like in a computer. I don't know. When I go to the doctor, they print me out a chart and it tells me where my boys are on the grand scheme of things. And so, but this is part of the analysis that goes behind it. All right. So now, sometimes things are not linear. They do not grow in a linear fashion or decay in a linear fashion. It is going to be important for us to be able to choose the appropriate model for this. So linear models are going to be used when you have roughly constant rates of change. So this would probably be a pretty good one to look at for a linear model while they're babies. It probably would not be good to look at this throughout a lifespan, because eventually this baby, it'll keep growing, but it doesn't grow at the same rate the whole time, right? You might grow faster at different points, and at some point you're going to top out and you're going to quit growing anymore at all. So there can be limits on when it's useful for that. But definitely in the first few weeks of life, this appears to be pretty linear. Quadratic. Notice here it says roughly linear rates of change or roughly symmetric with a single maximum or minimum context involving area. This is roughly linear rates of change. Remember doing that rate of change stuff where we did like the first difference and the second difference? So one thing you could do with your data, if it doesn't really look like a line very much, you could do your like first and second difference and see if that's looking kind of linear and see if that seems to fit. Also, definitely, if you see data go up and come back down, then it's likely that quadratic might be a good one for you to use there. Cubic is particularly helpful in contexts that involve volume, because volume has three different variables. Like if you think of a box, length times width times height, or a cube, x times x times x for that. So volume, this shows up. Sometimes cubic models are better than quadratic, but they don't make as much sense when we look at the regression model. So let's just think logically what should happen here. Determine whether linear, quadratic, or cubic would be most appropriate. So A says balloons are filled with water in preparation for an epic water balloon battle. Each water balloon is roughly spherical. The radius of each water balloon is measured relative to the amount of water it holds. So think about blowing up a water balloon. You could be, perhaps, maybe you have the great idea that my son had one night to take a regular balloon and make it a water balloon, like the big balloon. He was in our upstairs bathroom, upstairs, so he's not on the first floor. And he took a regular balloon and he filled it all the way up with water. We're talking, water balloon this big. And I think you can imagine what happened with this water balloon whenever he got it out of the sink after he got done filling it up. Popped water everywhere. It went down through the ceiling. I've got water dripping through my ceiling, in the kitchen where he has popped this giant water balloon. So, it's a bad idea. If you've been thinking of trying it, make sure you're outdoors whenever you do it, because he was grounded for a while over that one for not using his brain. But if you think about blowing up that water balloon. At the beginning, think about the radius. It's going to blow up at the rate that you're putting water in is going to be roughly the same. Like the sink is filling up the water balloon at roughly the same rate. So at the beginning, it's going to blow up and the radius gets bigger pretty quick. What happens if you're blowing up a giant water balloon at the end? That radius is like you put a lot of water in there, it just gets a little bit bigger, right? You can think of blowing up a balloon with your mouth too. Like you blow it up and it gets bigger and bigger and bigger, and like the last few breaths, it gets bigger, but not the radius is not growing nearly as much till it's about to pop, right? So in this case, it's not going to be linear. Linear would be like with every breath you blow into the balloon, or every minute that the water balloon's filling up, the radius is growing the same length. What context are we talking about here? Would this be talking about the area or the volume of that water balloon? It's your volume. Volume is most likely to be cubic. Oh no, I've just lost the stinking tip to this again. The answer there is cubic. Oh gosh. Read the next two and think about what you would have there. And here it hit the floor. Oh, that might be it. No, I think it is actually a piece of lead. It is about that size right there. It's so stupid. Also, lead.
Is that it? Is that the big propeller? Is that part of the test? I think this is the floor.
It's like perfectly camouflaged on this floor too. Okay, we gotta move on. I can't write down the answers. Y'all will have to write down what I say here. Totino's pizzas are on sale at the local grocery store. The price of the pizza varies between $1.99 and $2.19, depending on the variety. The total number of Totino's pizzas are counted relative to the total price of the purchase. So we're talking about number of pizzas you buy and total price. What's that one going to be? It's going to be linear, because if you buy 3 pizzas, 3 times the price, right? 4 pizzas, it's just going to be a rate. It's not going to be perfect, because maybe like the cheese pizzas are a little cheaper than the pepperoni pizzas, but they're pretty close to being the same. So that one would be linear for B, which I can't write down because I have lost the tip to my thing, and I'll have to search diligently here in a minute. C, a sprinkler is placed into a yard to water the grass. The sprinkler rotates in a circular pattern and waters all the grass between the sprinkler head and the furthest distance it reaches. The radius of the circular path is measured relative to the area of watered by the sprinkler. What do you guys think for that one? It's going to be quadratic, because area is typically going to be quadratic. Think about the area formula. It's pi r squared. That r is squared there. So that one is going to be quadratic.
It's also like the sprinkler like reaches out and like comes back. So it's like basically that's like come back over.
Yeah. Okay. Now let me see. We got 2 of these, and we're not going to have time to do both of them. Let's see. let's do 5. Okay, we're going to skip 4. All right. So, this has something special that I want you to see. The annual U.S. per capita total cheese consumption is shown in the table above for 1995 to 2020. This problem says, let the year 1995 be represented by x equals 0. This can be done with 1995 as 0, but it told you to let 1995 equal 0. So this one equals 0. That means when I go over here on my table, I'm going to start me a new table here, I should put 0 and 29.2. So if that equals 0, what should 2000 equal? 5.
Going up by 5?
Yep.
Oh, okay.
What about 2005? 10, 15, 20, and 25. So since it tells you to do that, you want to go up by 5s instead of, well, you're going up by 5s either way, but you want to start at 0 and go up by 5s. It's not always by equal increments. What you could do here is just take the year and subtract 1995 from it. So if they gave you like 2018, the 2018 minus 1995, you'll get the number there. And so if I type these in really quickly, because we are running out of time, here, it says we're supposed to be finding a linear model for this. I'm going to hit this so I can see. It looks fairly linear here. So if I want to do a linear model, I'm going to do y1 squiggle a x1 plus b. And that'll give me a linear model. I'm interested to see what quadratic does. It didn't ask me to do this. For quadratic, you do ax1 squared plus bx1 plus c. When I want to compare these, I look at my r squared values right here. R squared for this one is not 0.97. R squared for this one is 0.969. The quadratic is very slightly better. But if you zoom out, notice like cheese consumption takes a downturn here. Now, first of all, this is 200 years away from now. It's probably not a good idea to make predictions on cheese consumption that far out. But you might need to consider other data to choose which one. This one told us to do linear, so I'm going to do linear. Okay. You would write down your equation here. And then when it wants to know for the year 2013, what do I need to plug into this? I'm not going to do 2013. I need to do, I'll do 2013 minus 1995, which is going to give us 18. So I would do x equals 18. And then if I look at that, it crosses right here. So I'd get 36.582 for that. And then if we want to know cheese consumption for 45, we would type in y equals 45 for that, and we would look over there. Okay, so your worksheet is going to ask you to do similar things here. Like these back. You can go ahead and start packing up.
Wait, sorry, so on C? Are you plugging in for X or for Y?
Y, because cheese consumption would be Y. In that case, it would be Y equals 45, and you'll look for where they cross.